Well, it's a very great pleasure for me to introduce Kevin Costello. I've known him since he became a graduate student in Cambridge in just a year. I moved to Cambridge, I think, in 1999. And the first thing that I noticed about him was his complete unobtrusiveness. This was a two-sided thing. He also doesn't remember whether he came to my lectures. So at first we knew nothing of each other, but after a couple of years, I suddenly noticed, as well as the unobtrusiveness, that he came and told me a little bit about his work, and I was just amazed. There'd been this person moving around in front of me who knew so many things that I didn't know and knew them so much better than I did. And that was the beginning of a series of events in which all my own mathematical heroes, one after another, sort of discovered Kevin. I think the first was Dennis Sullivan, and then Edward Witten, then maybe Maxim Kontsevich, and so on and so on. And presently there was this bidding war for Kevin, and he decided to go to the Perimeter Institute. Anyway, I won't tell you anything more because you're here to see him bat and not to hear me bowl, and I'll leave the talk to him.
Thanks very much, Graham. So I'm kind of excited for the conference that starts tomorrow, which celebrates Graham's 80th birthday. And I think the last time I was in Oxford might have been for Graham's 70th birthday. Oh, and he hasn't changed. But yeah, as Graham said, I've known him a very long time. When I was a graduate student and a postdoc, when I was a postdoc, I would come up to Oxford on a pilgrimage to learn from Graham. And he was very patient and explained many things, many very basic things. And of course, Graham's perspective. When I started at Cambridge, I wanted to learn quantum field theory, so I went to the courses in part 3 about quantum field theory. If anybody, mathematician, has been to those, of course, this did not last long. It just, nothing made any sense. But I was lucky to learn how a mathematician should think of this subject from Graham, and I was much more lucid. So, of course, he's been a great influence on me. So, what I'm going to try to talk about today is something I've been kind of excited by. I'm going to try to make it very extremely elementary. So it's a relationship between, well, this is a little funny, scattering amplitudes and so scattering amplitudes are typically kind of complicated things, and something which is pure algebra. So I find this exciting because this is hard, and algebra is easy. I think this is really a true fact about mathematics. Analysis is just hard. So I should start by explaining a little bit about what scattering amplitudes are. Oh, by the way, is my handwriting big enough to be legible? Yeah, OK. So if we have a quantum field theory, the scattering amplitudes is a function of n momenta. How does this thing work? So the PIs, they are in, I'm going to be discussing a 4-dimensional quantum field theory. And I'm going to take them to be complex, so they're in C4. they're null vectors, and the sum of them is 0.
Can I ask very basic questions?
Yes.
First, why are you assuming the momentum to be complex value?
Well, the Hilbert space is a complex vector space.
I mean,
Right.
physical momenta are always real values.
It depends on the signature, right? I want to be able to analytically continue between different signatures, and at some point I might choose them to be real. I also wanted to understand the analytic behavior of the scattering amplitudes. It's an analytic function. You really want to consider it on some real slice, but it's useful to understand its analytic continuation and the poles that has.
It's more like fundamental question, but you said if you have a cavity, but what is a cavity like? How do you construct it?
No,
Oh.
I think we can keep this question to the end.
Yeah. Well, I'll explain I'll give you some formulas in a minute, some examples. So this defines an affine algebraic variety. And the scattering amplitudes S is going to be is an analytic function on some domain. Now, typically, it's super complicated. If you look at the literatures, for classical scattering amplitudes, it'll be a rational function. But as you go down to look at the quantum scattering amplitudes, people do computations, and they almost immediately run into polylogarithms and all kinds of transcendental functions. Well, let me explain how to compute them in a very simple case. Let's take the phi cubed theory, where the Lagrangian looks like that. So I'll describe the rules for computing the tree level, that's the classical scattering amplitudes. And this is going to have a formula as a sum over trees of something. For example, when n is equal to 4, it's going to have 3 contributions. And they'll look the same, but they're going to differ by how I've labeled the edges. P3. So the rule is the following. Firstly, you orient your tree arbitrarily. Like that. For each edge, you define the momentum on that edge, so conservation of momentum holes. So basically, we have an oriented tree. The momentum at each edge is the sum of the momenta flowing into that edge. So here, in the first example, PE is P1 plus P2 in this example. And then we take the product of the edges, 1 over PE dot PE. OK, this is a very simple rule. And what we find for the 4-point amplitude is that it's the following rational function. Okay. So this is all something you would see in maybe a first quantum field theory lecture. Factor of 2, yes, thank you. Well, what I'm really going to be interested in, so I want to relate these to something in conformal field theory. I'll introduce that in a minute. But the key to the relationship is to understand the singularities in these amplitudes when two momenta become such that their inner product is 0. So you notice this has poles. Now, the formula for the, even at tree level, the formula for the 10-point scattering amplitude is some kind of combinatorial mess. But the poles have a nice universal behavior.
Is the inner product in Costello Euclidean?
It's complex. It's a complex bilinear form, valued in C. My momenta has been analytically continued to C4. So the inner product is a complex linear map from C4, tensor C4 to the complex numbers. So if you can choose different real slices and you get Euclidean or Lorentzian as you like. So this is the analytic continued amplitude. And for loop amplitudes, you do have to worry about this kind of stuff. But for tree-level amplitudes, when it's a rational function, it's all trivial. It doesn't matter. So the poles have a universal behavior. In the following way. If I take any amplitude like this, it's going to behave like as, let's see, near the divisor where pi dot pj is equal to 0, it looks like something called a splitting function times an amplitude pi plus pj pn. So this tilde means plus terms which are regular on the divisor. So this is, of course, a useful relationship, but the main reason I wanted to write it down is that, okay, this is a math audience. Maybe you've never seen scattering amplitudes, and this is a weird thing. This quantity is a very simple mathematical explanation. I'll explain how to do it for a scalar field, and then we'll just compute it for gauge theory, and it's a kind of a fun computation. So how do we understand the splitting function mathematically? So we first notice, if I set phi, well, we can understand this using the equations of motion. So the equations of motion are Laplacian phi plus phi squared is equal to 0. If I set phi p is e to the I p dot x, and if epsilon is square 0, well, then epsilon phi p satisfies the equations of motion. Obviously mod epsilon squared. This is just saying this satisfies the linearized equations of motion, and it does that because I'm assuming p is a null momentum. So how do I do the splitting function? I'm going to take two solutions of the linearized equation and combine them into a solution to the full equation. So let's look for a solution to the equation of motion, which goes like epsilon phi p plus delta phi q plus epsilon delta something So I'm working modulo epsilon squared and delta squared. So there's this epsilon delta term. And we can just solve the equation, and the result will be the splitting function times the state plus q. This is a general procedure to understand the singularities and scattering amplitudes. We start with two solutions of the linearized equations, extend them in this way to a solution of the nonlinear equations, and then there's a piece which will tell us the singularities in the amplitude. So let's do it in this case.
So what are the P and the Q? No, the phi is a function of P.
I should say phi is a function of both a momentum and a point in space-time. Is that better?
Okay. And then the solution is also Q.
Well, I take two different momenta, P and Q, and then if you calculate this solution, it looks like, well, it has to have this, the momentum has to be the sum which you can see if you think about the Fourier transform, times some function of p and q. And it's that function of p and q that I'm interested in. So of course, we can do it explicitly in this case, because we know the equations of motion. So what we need is that the Laplacian of the splitting function pq times e to the I p dot x e to the I q dot x plus e to the I p dot x e to the I q dot x equals 0. So I take the Laplacian in here, I get a factor of 1 over p dot q. Oh, sorry, p dot q. So okay, I'm not sure I explained that super clearly, but it's extremely elementary. So what I want to do next is I want to explain, if we do this for gauge theory, we see some relationship to conformal field theory. So I'll get to explaining what a conformal field theory is following Graham in a little bit, but let me try to explain how we do this for gauge theory. And again, this is entirely elementary computations with PDEs. So we have to understand what are the states of Yang-Mills. In general, states, like single particle states, are solutions of the linearized equations of motion. So for a scalar field, solutions of the Laplace equation. So for Yang-Mills, there are two types. Positive helicity, which is a connection A, which satisfies the self-dual part of the curvature vanishes, and negative helicity, which is the same kind of thing. So in each case, positive helicity states and negative helicity states are each parameterized by a harmonic map phi from or 4 to the Lie algebra. Yang-Mills gauge theory depends on the choice of the Lie algebra. If the Lie algebra was OR, then the states are parameterized by two harmonic functions.
Do these states belong to some kind of a physical Hilbert space?
Yeah, so the single particle states are the physical Hilbert states.
Those connections, so you mean that those connection A's, they belong to some kind of Hilbert space?
Yes. I mean, these are this, I'll write A in terms of a function. This function will be e to the I p dot x. That will be the state of momentum p, of positive velocity or negative velocity. So one can ask, how do I build a solution to the Yang-Mills equations based on a function? Well, fortunately, this kind of thing was done by C.N. Yang of Yang-Mills and Yang-Baxter and many other things in, I don't know, the 50s or something like this. And what Yang did is the following. Choose a complex structure and then, given a function, or for to my group, my Lie algebra, we define A equals e to the minus phi d bar phi. That should be e to the phi. So then one can check that 1 plus star dA is equal to 0 if and only if the Kähler form times del e to the minus phi del bar e to the phi is equal to 0. So this is a nice equation called Yang's equation. And let's expand it out in phi. So I wanted to say at the linearized level, it looks like, a harmonic function. And we'll see this if we expand it out. The equation is Laplacian phi at e minus a half del phi del bar phi times the Kähler form plus cubic and higher terms. I feel like this all went much quicker in my notes. This always happens. So what have we learned? Well, we've almost learned how to figure out the singularities in the tree-level scattering amplitudes of gauge theory by saying, oh, look, my state is parameterized by a harmonic function. And then I look at this equation, and I say, if I have two harmonic functions, I try to combine them so that they solve the equation including the quadratic term. And I'll find some pole, and that will be the singularities in the Yang-Mills amplitudes. And when we'll do this, we'll see something really neat. But to see the really neat thing, I need to tell you, I need to choose coordinates on the space of momenta. If I take complex momenta, well, mod scaling, this is a quadric in CP3. And everybody knows the quadric in CP3 is a product of two CP1s. And this fact is related to the exceptional isomorphism of Lie groups. Spin 4 is SL2 cross SL2. Each copy of SL2 acts on one of those two copies of CP1. So I want to choose coordinates in the space of momenta that are compatible with this decomposition. And I do it as follows. Momenta are linear functions we let u1, u2 be holomorphic linear functions. And then I set my momentum to be, the space, this cone is of dimension 3, so I need 3 coordinates. I'll call them z, lambda 1, lambda 2 is equal to these are coordinates on the null momenta. Maybe I'll go over here. So why are we doing this? Well, let's now do the very simple exercise of saying, given states with momentum parameterized in this way, let's try to combine them into solutions to Yang's equation. If we say phi z lambda 1 lambda 2 is e to the I p dot, p lambda 1 lambda 2. It's also going to depend on an element of the Lie algebra. Okay, so let's solve Yang's equation, which I wrote over there, mod epsilon squared delta squared, where we start with epsilon phi plus epsilon plus delta phi w u1 u2 y, and then I'm going to solve the equation. I get epsilon delta times something. Anybody can just go compute this. It takes 2 seconds. Well, the answer is really nice. 1 over z minus w phi z lambda plus mu x y. Okay, so I'm hoping some people have noticed the cool thing. That is that the poles in the Yang-Mills tree-level amplitude are equal to those, the poles in the Cass-Moody algebra. Okay, I know this was a very general talk, so I wanted to very quickly explain. I'm actually kind of glad that the audience is a little smaller than for the last talk. It's a bit less intimidating. I wanted to explain a little bit about what this object is, because I can't assume people have seen it. So let's take Graham's picture. So a 2D CFT assigns a vector space V to the circle and a linear map to a cobordism. For example, if I have a cobordism like this, this will give you a linear map. This is at 0. This is at z. This will give you a linear map mz, v tensor v to v. There is a special 2D CFT called chiral. Well, it's not strict, it doesn't satisfy all the axioms, but let's not worry about that. The chiral WZW model, it has the following feature, that there's a linear map J from a Lie algebra to V such that mz of j of x, j of y looks like a 1 over z squared times a number called a level times trace xy plus 1 over z times j, the commutator. And these formulas are like the same. So in a CFT, we have correlators V tensor n to C, which are associated to the 2-sphere. Where I've removed n circles. I'd say these points are centered at z1, z2, up to zn. And if OI are elements of V, then the correlator.
I have a question. So you're saying that these two formulas are the same. I mean, I see that they're similar, but
Yes.
I don't recognize all the terms of the one below up above. For example, the first one corresponds to
It's level 0.
or level 0. Okay.
Yes. I mean, you can get the level, but to get the level, you have to work in a very particular curved four manifold. It's called the Burns metric.
It's called what's the curved manifold called?
It's called the Burns metric. Okay. It's a scalar flat Kähler manifold. And the other thing you might object to is I had these two parameters lambda and mu, and they're not here. But I'll explain that in a sec. So if I have a CFT, you can look at these correlators. And these have poles which are given by these things I've called mz, just like amplitudes have poles given by the splitting function. So we see things are very similar. In each case, we get a function of a bunch of variables with a similar polar structure. OK, so maybe let me just say the precise statement about how these things are the same, and then pause for questions. So the precise statement, which is due to Guevara, Himwich, Pate, and Strominger, is that the splitting function of Yang-Mills at tree level is given by the Cass-Moody algebra at level 0 for the infinite dimensional Lie algebra G lambda 1, lambda 2. OK, any questions? Mm-hmm.
Other devices with some of several vectors that's non-zero.
Yes, that doesn't happen in that. If I took, for example, the phi-4 theory, it would not have any poles at tree level when two amplitudes are collinear, but it would have those poles. But that does not happen for self-dual Yang-Mills. OK. So this leads us to a natural question. Which I have left? So are amplitudes CFT correlators? Well, to answer this kind of question, we also need to think about what about the states of negative velocity? And we also want to think about, this has been mostly at tree level, loop level amplitudes. So the answers to all these questions is, well, QCD is like super hard. It's incredibly complicated, and it's way too much to hope for that anything like this would just work for everything. But there's little bits of QCD for which it does work, sometimes. So let me try to explain the kind of simplified version of QCD, which knows a bit about the original theory, and for which this does work. So the first thing I have to say is for 2, this will cause problems. Because if we use the equation that f minus is equal to 0, then we would find 1 over this kind of pole. So this is kind of bad. Okay, if you want to have a vertex algebra living on the z-plane, you don't want to have a pole in this way. That just doesn't make sense. So the solution is to work with something called self-dual Yang-Mills. So this has two fields. A, which is an ordinary gauge field, and B, which is an adjoint valued self-dual 2 form. And the Lagrangian is the integral of B wedge f of A. So it's a standard thing. I think possibly Chalmers and Siegel were the first person to write this down in the 90s, but it's kind of very easy. If we add integral trace b squared term, we get full Yang-Mills. So self-dual Yang-Mills is a kind of simplification. So if you play around with the Feynman diagrams, you can see this knows about some things, full Yang-Mills, but not everything. OK, so if we do this, we've removed the problematic f minus equation. Well, really, we've linearized it. So we don't run into that problem. And what we find, maybe it's kind of a lemma, that the amplitudes at tree level for self-dual Yang-Mills are controlled by the Cas-Moody for G plus G star join two variables. So if I had to replace my algebra by my algebra plus the co-adjoint representation, and strictly speaking, I mean something a little more general than amplitudes to get a good answer here. Something called form factors. OK. Maybe let's address this third question. So this is where the story gets kind of fun. So one theorem, kind of a physics theorem. For quantum self-dual Yang-Mills plus matter, which I haven't discussed, but we're going to need it, there is a deformed vertex algebra controlling amplitudes if and only if the trace in the adjoint representation of some element to the fourth power is equal to the trace in the matter representation of x to the 4. So for example, G is SL3, or is 8 copies of the fundamental, sorry, 9 copies of the fundamental plus 9 copies of the anti-fundamental. This is kind of annoying because in the real world, there are 3 copies of the fundamental and 3 copies of the anti-fundamental. But, you know. The proof, well, I won't give you the full proof, of course. One implication, we give a twistor construction of the vertex algebra. And the other implication, physicists write formulae for the one-loop splitting functions. Sorry, I think I'm going a little fast. So you go read the physics literature, people who study amplitudes. There's a paper of David Costello from 1994 who will give you a formula for the one-loop splitting functions. And then you say, OK, let's try to turn this into a vertex algebra. And a vertex algebra, it satisfies an associativity condition written by Borcherds. So you ask, does this satisfy the Borcherds condition? The answer is no. But you can, so the splitting functions are the leading order singularities. You can correct by a subleading term to make it satisfy the Borcherds identity, if and only if this holds. Okay, and maybe just the very last thing, because I know it's lunchtime and everything, but so the part I'm most excited about, I think, so we can show in these cases QCD amplitudes up to 2 loops are vertex algebra correlators. And so you can compute them with algebra. So there's this really fun game where you take the vertex algebra, which is some explicit OPEs, and you compute its correlators using some inductive thing. And you get some expression, some rational function. And then you go look at what people computed maybe 20 or 30 years ago. And after some work, the expressions coincide as long as this trace identity holds. 2 loops is an exciting case because, well, the algebra becomes difficult, but the quantum field theory becomes really difficult. So at one loop, this method gets you to the cutting edge around 1994. But at 2 loops, it gets you to the cutting edge around 2020. So I'm kind of excited for that part of it. Okay, so I'll stop there.